This is the makeup lab for OPTI471B Lab 3 Gaussian beam imaging by Group 1A.
In the previous lab, we gained a better understanding of Gaussian beams and their beam profile. In this lab, we will further this understanding by seeing what happens when we send a Gaussian beam through a lens. To do so, we will work with components such as Keplerian, beam expanders, spatial filters, and shear plates. Using these parts, we will image the beam waist along the optical axis and measure the new beam profile of the imaged beam.
A Keplerian beam expander is an afocal system used to change the size of the beam. It functions with two positive lenses placed the sum of their focal length apart. The size of the beam will change by the system's magnification, which is given by the ratio between the focal length and the second lens to the focal length of the first lens. In this lab, we are required to have magnification of at least 10x. Ideally, we would use the 16mm focal length objective with a 160mm focal length collimator, but with limited available optics, we used an f1 of 16mm and f2 of 200mm, resulting in magnification of 12x.
In order to test that our beam expander is working properly, we used a shear plate to verify the beam's collimation. The shear plate creates an interference pattern by overlapping the original beam with a laterally shifted copy of itself. If the beam is perfectly collimated, the resulting wavefronts are planar, and the fringes appear as straight, evenly spaced lines parallel to the reference line on the viewing screen. If the beam is diverging or converging, then the fringes appear tilted or curved. By adjusting the position of the second lens in our beam expander and observing the fringe pattern, we can fine-tune the lens position until the fringes are straight and parallel, indicating that the output beam is collimated.
At the intermediate point of the beam expander, it is useful to have a spatial filter to eliminate any spatial noise of the Gaussian beams caused through scattering through free space. It is important to choose a spatial filter that properly filters unwanted spatial frequencies while also transmitting the maximum amount of signal. To do so, we must find the optimal spatial filter diameter using the original beam waist, wavelength, and focal length of the first lens. We found that our spatial filter should have a diameter of at least 26 microns. Due to limited resources in the lab, we must use a 50-micron spatial filter.
We carefully adjusted the XY position of the pinhole to center it on the beam and used the translation stage to fine-tune the axial alignment. A properly aligned filter should transmit a clean, symmetric beam with minimal diffraction artifacts, and we verified this visually and with power measurements. This alignment step is critical. It ensures the expanded beam is free of spatial noise and ready for collimation.
After confirming that our expanded beam was clean and collimated, we added the 400mm focal length focusing lens. According to Gaussian beam imaging theory, when a collimated beam passes through a positive lens, the beam focuses at the back focal point of the lens. If the input beam is well collimated, this point corresponds closely to the location of the new beam waist.
After our spatial filter is properly aligned, we compare the laser power at several key points in the system. After the spatial filter, we measured a power of 1.7 milliwatts. After the beam expander, the power increased to 2.5 milliwatts, and the focus point within the beam expander, it peaked at 2.569 milliwatts. This increase confirms that the spatial filter was properly aligned and that minimal power was lost, suggesting that the majority of the Gaussian beam's energy passed through the pinhole.
We then aligned a microscope with a 20x objective to be used for precise position measurements of the knife edge. This high magnification was crucial for accurately detecting the beam's edge during the knife edge scan method, which we used to determine the beam radius at different positions. Proper alignment of the microscope ensures that the field of view is centered on the knife edge and that the focal plane coincides with the laser beam's path.
We then began the knife edge beam profile scan. We took measurements both in front of and behind the beam focus to capture the beam's radius, W of Z, at different positions along the propagation axis.
Using the microscope-aligned knife edge, we recorded the power drop as the blade moved across the beam. By fitting the resulting data to the error function, we extracted the 16% and 84% transition points to determine the beam width at each location. According to the lecture, the method provides a reliable way to measure the beam radius because the Gaussian intensity distribution maps directly to the knife edge's power curve. From these measurements, we generated a plot of WZ versus Z and verified that our beam follows the expected Gaussian propagation behavior, confirming a well-focused system.
For our results, we performed a knife edge scan at the focus of the imaging system. At a knife edge position of 82.2 centimeters, we recorded the 16% power point at Z equals 3.21 millimeters and the 84% power point at Z equals 5.91 millimeters. Using the knife edge method, which captures the transition across the Gaussian beam's intensity profile, we calculated the beam radius using the formula WZ equals Z of 84% minus Z of 16% divided by 2, which is 2.7 millimeters.
At the second knife edge position of 130 centimeters, we measured the 16% power point to be 1.17 millimeters and the 84% power point to be 1.39 millimeters. Using the knife edge profiling method, the beam radius is then 0.22 millimeters, and additionally, the distance between this focus and the previous one was 47.8 centimeters, which is our delta Z value.
To determine the beam waist position, we used a theoretical equation derived from Gaussian beam propagation. This expression relates the measured beam radii at two positions and the wavelength to solve for Z0, the Rayleigh range, where the beam waist is located. We calculated two possible solutions, 5.41 millimeters and 7.47 millimeters. Based on our measurements and physical setup, only one is physically meaningful.
Since our two knife edge measurements are on opposite sides of the waist, we use the top expression for Z1 with a negative square root and the standard formula for Z2. This allowed us to solve for delta z, which was z2 minus z1, which should match our measured separation of 47.8 centimeters, confirming our solution is consistent with both theory and experiment.
To verify which z0 solution is physically valid, we back-calculated delta z using both possible values. The first solution of 5.41 millimeters gave us a calculated delta z of 477.99 millimeters, which closely matches our measured value of 478 millimeters. Since this aligns with our experimental result, this confirms that z0 does equal 5.41 millimeters, and this is consistent with both theory and the lab procedure.
Using our calculated value for the Rayleigh range Z0, we solve for the minimum beam waist W0 using the formula W0 is equal to the square root of lambda times the Rayleigh range divided by pi. This gave us that the beam waist is 0.03301 millimeters. When applying the beam imaging formula from lecture, for W of f prime equal to lambda times f divided by pi of W0, we calculated the beam waist at the focal point of the imaging lens to be 1.562 millimeters. This confirms our system expanded the beam as expected before focusing.